let's start. We had on Tuesday discussed the Schwarzschild metric. I at least introduced it, and I told you that today is essentially devoted to a further discussion of that metric. So we would like to make sense of what it tells us and see some implications, some interesting implications, and some that will keep us busy also for next week. So I may have mentioned, or it may already be clear to you, that the Schwarzschild metric is essentially the metric that describes space-time around a spherically symmetric object. And this object can just be an ordinary planet like Earth. And then the metric is valid, or the solution described by the metric is valid outside of the Earth. Or it can describe an object such as a black hole, which is also spherically symmetric. So let me start reminding you of something we did at the very beginning. So here's a black hole. You may have seen a picture of this object. I think it was very famous when it's a very famous picture, and it was considered a big breakthrough that experimental astrophysics were able to actually take such a picture. So it's nice for this theoretical course as well that you have something on the left-hand side where I usually told you that's the real thing. And remember, this was in our discussions of the manifold, that was the actual manifold. And then we talked about charts. And what we have done so far is introduced one particular coordinate system, the Schwarzschild coordinates, which are in the spatial direction r, as well as spherical coordinates, which I don't draw, and in the time-like direction we call it t. Now we could ask, what do different things that we see in the real world look like in this chart? Now if you look at this real picture, then there's something like a horizon here in the very middle. So the very middle, there's a black region, and I now drew a boundary around that black region in the middle. And that's essentially a sphere in space. Now, how does this look like in our diagram? In a diagram, because we have spherical coordinates, and because it's a sphere, as I said, and we choose the center of the coordinates, at least in our imagination, in the center of that black hole, where we would believe the center is. So we'll see that it wouldn't make much sense to talk about the center in the usual sense, but we can say there is a coordinate system in which, if we extrapolate, there would be the center here in the middle. And in this coordinate system, it's just a point. Yes, there was a question. Okay, is there a question? Okay, if not, let me continue. So the sphere, this thing I drew is at any point in time just one point here in the diagram. It has a particular radius, r, so it's a point. But of course, if we assume the black hole stays there over time, this radius remains the same. So we have a line up. So just to remind you, I mean, this in this spatial picture, that would be a two-dimensional surface. And this two-dimensional surface is here just essentially at any point in time. So if I make a slice here in time, just one point, but because I have here a space-time diagram, it's a line. It's essentially the vertical line of that horizon. And that's called, by the way, I will refer to that as the event horizon or Schwarzschild horizon. That's always the same. It's the point where we identified already last time that we have a singularity in the metric. And remember, this occurred at the point where r is equal to 2n. Of course, at this point, it's not yet clear why this is an interesting point. I just told you and even emphasized that that's just something in the metric that is special. And indeed, we will see it's just a metric. It's an artifact of our choice of metric that it looks like it's a singular point. There's no singularity there. Nevertheless, it's a special point. It's actually the point, as we will see, where it's essentially the point of no return. So if you cross that point, and even if light crosses that point, it will not come out again. And that's why the interior of that looks black to us. but that we will discuss once we have introduced more convenient coordinates, which we will do today. So just as a small reminder, and because we are going to use it, the metric in this particular coordinates look like this: 1 minus 2 gm over r dt. Let me abbreviate it. It's just dt tensor dt. And then we have the spatial component, which looks, which has a term that looks the same but is inverse, and that we call dr2. And then there are further components for the spherical. There's essentially the spherical part, which I'm not going to write again. We had done that last time. Now, like in manifolds, we can choose different charts, and that's what we are going to do today, and what we have actually already done in the exercises. So if you have solved the exercises, then essentially what you did in this manifold picture is to create a different chart. This chart has different coordinates, names. I will call it now X and T, and let me write here title. So the first chart was essentially the Schwarzschild Coordinates, and the second one is the Kruskal-Szekeres. So remember, it's the same metric, so it's the same physics that we are describing, but with different charts. Now the question is, how do now things like this line, this event horizon, how does this look like in this chart? And as we are going to see, it will look very different. It will actually look like this. It will be essentially a diagonal line. So it's the same line as above, it's just represented in a different chart. Now you see there's already something kind of strange here, and you should already be aware of it, that it's not clear that in this chart, in the Schwarzschild chart, T, the coordinate corresponding to T, is always a time-like coordinate. I mentioned last time that this is only true outside here, but not inside. And the reason for that is easy to see when you look at here the definition of the metric. If this first term here is negative, then of course it's like a spatial coordinate. And you see that at the same time when this becomes negative, this term here will of course become positive. So this turns in the r coordinate turns into a time-like coordinate, meaning that the direction vector as you change the coordinate r is a time-like vector. And there's always one time-like coordinate that we have. That's of course because of our Lorentzian, so every metric in a space-time is Lorentzian, as we said, and this has signature 1 minus 1 minus 1 minus 1, so there has to be always one that is time-like. Okay, so the overall idea, that was now a very smooth introduction, but the overall idea is the following. At the end, what we want to understand is this object here. We want to understand what happens in real nature. However, this is hard to picture. Of course, that's a picture, but we don't really see what's going on here, in particular close to the horizon. So what we are going to do is to represent that real object in charts. Like when we have an atlas of the Earth's surface, we are representing the real thing in charts. And the question is now, what are good charts? What are charts that give us a good and provide us with a good intuitive picture of what's actually going on in reality? Now we would say, and that's indeed the case, if you're looking at things from different observers' perspectives, there may be also different charts which are useful. And indeed, if you want to have something that is close to the perspective we are now in as we observe from the far outside this black hole, then these Schwarzschild coordinates are actually quite a good choice. At least it's already capturing the intuitive fact that this horizon just stays at a certain place. However, for an observer who is very close to that event horizon, so someone who is just essentially hovering above it, it turns out that this choice of chart is a very bad one, and the Kruskal-Szekeres will be much better. So what does better mean? And to explain you what it means to have a nice chart, let's ask ourselves how things move. So of course we are talking about how things move in the real world, but how do things move in the chart representation? One thing we can do is essentially to ask ourselves, how would light move? And you know, light always describes a cone. So if I'm here far away from the black hole at some point, which I draw here in orange, and ask myself, how does a light ray behave if I shine it radially into the direction of the black hole? Then it will just move like this in a 45-degree line, essentially, because I told you already last time that the Schwarzschild metric far away from the black hole looks like the Minkowski metric. So it's just, things are essentially flat, and the coordinates can be identified to the lowest order with the Minkowski coordinate. Similarly, if I shine a light ray that points away from the black hole, I just get another 45-degree line. And so essentially everything, even in particular massive objects, will of course somehow move within this boundary. So because nothing can move faster than light, if I fill the cone, this is essentially the area that is reachable. This is sometimes also called the causal future of that point. So if I'm at that point, I can ask myself, which points in the space-time can I reach? Where can I send a particle to? And this is essentially the set of points described by this cone. It's of course an open cone that continues forever. Now, this was a cone far away from the horizon. How does such a cone look like when we are close to the horizon? To understand that, it's maybe useful if I look at the metric again. So let's maybe for simplicity just give this term here in the metric a name, b, and then this here is b to the -1. And now you could ask ourselves, what would a light ray look like? What's the kind of direction of the cone? My claim is now that in these coordinates, so I just look at now the t coordinate and the b and the r coordinate. If I had a vector of this type, so if I had something in the direction 1b, meaning it's the first component corresponds to the t and the second to the r component, that this is a vector that is light-like in this metric. And that you can easily verify if you multiply this vector essentially with the metric from the left and to the right. I mean, this is just shorthand for evaluating the metric on the vector given by these components in this particular chart. Then we can evaluate this. So this is essentially g of that vector, because g, the metric is given by this matrix here, that obviously gives 0. So this means that if I go 1 unit into the time direction and by b into a spatial direction, then this corresponds to how a light ray moves, because a light ray, of course, as you know, has a direction vector which is always a light-like vector, and a light-like vector is one whose metric is 0. So these are vectors of metric 0, but how do they look like in the diagram? So if I'm close to the event horizon, then the value b becomes very small, because you see, if r is close to 2gm, then obviously this whole term is small, which means that a typical vector close to the horizon, if I go 1 unit up, goes only very little to the left. So a cone may look like, of this point may look like this, and then again to the right-hand side like this. That was even maybe exaggerated. It's maybe even more closed. It's maybe a cone like this. So it becomes very narrow. And that's true for all cones that are close to the horizon. So all these cones look like this. And of course that how close they are somehow depends on how on their distance from the event horizon. Okay, now I could even ask, how do things look like within the region in the left, so in the part which is essentially beyond the event horizon from our perspective. And if I look at that, then of course I have a very similar behavior. I get essentially cones of that type, but now I have to be careful. Actually, I was making a simplification because I was already knowing which part of the cone is the future. In principle, a cone is a two-sided thing. So it's something like this, and I could say, this is a part, this is the causal future, and the other part is the causal past. But what I calculated is just these lines. So I somehow knew from these lines that this part here is the causal future. But now if I do that in the inside, I still get lines of this type, like this. But now I have to still determine what is the causal future and what is the causal past. And this turns out to be not as easy, but what is clear is that it cannot be that, for example, this region here that I've now filled would be would correspond to a time-like vector, because I told you the time-like vectors are more in the direction of R. So actually we would have to expect that actually this part here, in that part, or maybe the opposite, that we still have to find out, corresponds to the causal future. I mean, again, this can be seen, for example, by just thinking of a vector that purely goes into the direction of R. And if you insert that into the metric, then you see that in the region where this term here is negative, if you go only in the R direction, then you still get a positive term from here, because that this bracket is negative, so the whole thing is positive, so you get something positive. Whereas if you have a vector only going the t direction, then you get something negative. So a vector in this direction would be a spatial vector. So the time direction is actually like this, looks like this. Okay, so something strange happens at the event horizon. So here, if I draw trajectories, which I may also do, so I could now assume I have a particle somewhere close to the horizon, and this particle, let's suppose I take something which actually falls in. But because it falls in, it can, and assuming it's massive, it cannot move faster than the speed of light. So it has to be less and less tilted and has to approach this line. But it can never cross it, because it will always have to be within the light cones here. And these light cones become more and more narrow. And accordingly, this green world line will get closer and closer to the event horizon, but not pass it. So that would be a possible world line, something like this. There are other world lines of outgoing rays. So this is something like that comes from the direction of the black hole towards us, if you are standing away from it. So these are the lines. Now, the lines inside of the event horizon, let me call it inside the black hole, would need to have directions, for example, like this. So these would be valid trajectories. I mean, we'll see, because the things become flatter. I mean, that's probably a correct picture. That's what they can do. Typically, one looks at light, and then for light, it may look like something like this, for example. Obviously, we don't know what, I mean, we simply don't cover this part. That's excluded from the chart. So in principle, I cheated a bit in this picture. These are actually two different charts. One for this region and one for this region, which I just represented in the same picture. But the picture actually makes clear that there's a discontinuity here. So I better draw them as different charts. So think of this line as actually separating two charts, which somehow carry the same names. Okay, so that's what you have. And you see the problem with this chart. So these light cones here get very strange, and then they suddenly flip somehow. So that's not very nice. That's certainly not a good condition to understand exactly this region, the event horizon. So what we are going to do, and that's essentially our goal, is to have something that in the vicinity of the horizon looks still nice. For example, it would be nice if the light cones here would just look like ordinary light cones, like 45-degree angles. And we will see that this is actually possible. So the Kruskal-Szekeres coordinates are coordinates in which indeed light cones in the vicinity of the black hole horizon look like ordinary light cones. And then, of course, it means that an object, even a massive object, may legally move like this, because now its direction vector is always contained in the light cones. So it's perfectly fine if it moves like this. You see, this gives us a much better picture of what's going on, because if something is falling into the black hole, we would expect that at some point it crosses this horizon. But here, this horizon is just not part of the chart. So we don't see the interesting part where it crosses it. So that's essentially what the goal of introducing new coordinates. Now we have to get into a bit more technical considerations, but that's essentially an overview of what we are going to do or what we are generally doing when we are describing a black hole. Okay. Of course, we will come back to these diagrams and try to understand them once we have more precisely defined what they are. And despite the fact that this was done in the exercises, I will essentially give you again the definition of these coordinates. So I try to make the course as self-contained as possible, but I will not give a full derivation of them. So if you want to see how how you get, what's essentially the chart transformation from here to here, I will just state it. And then to, for example, calculate the metric and so on, that's something that I leave to you, but that's essentially a straightforward calculation. And if you did the exercises, it will be a very easy calculation. But before I now continue, let me do a few things that will simplify my life. So the first thing that I already wanted to do last time, noticed I had some confusion because of that, was I wanted to set the gravitational constant equal to 1. Actually, okay, because this is a course on GR and gravitation is the main topic, I should maybe at least once, before I set it to 1, say what it is in the units we are usually using. And that's probably an appropriate thing to do. It happened to me once, actually, when I went to a conference in the US, that I was asked the guys at the board always ask you, what is your profession? And I said, I'm a physicist. Then the guy said, oh, can you tell me what is h bar? And I said, oh, h bar, this is just equal to 1. This was not a good idea. I was then captured for 2 hours being interviewed and even had to present the talk. So if the same happens to you with G, tell them this number and not 1. It's meter to the 3 s squared kilogram. So that's essentially the number you probably learned I think even in high school when you do Newtonian gravity. That's usually the constant that is named there. Now, what we already did so far many times, and maybe I will comment on that again in the future, we set the speed of light being equal to 1, which at least allowed us to identify meters and seconds. But to do that, so to make this compatible with what we want to do is actually to say that if you didn't set c equal to 1, then you could, of course, consider the quantity g divided by c squared, which would be a more natural quantity because it somehow gets rid of this m to the 3, meter to the 3 and seconds to the power of 2. And then you see you get something, okay, now I don't want to calculate that to any digits, but of the order of magnitude of 10 to the minus 27 meter per kilogram. There's some prefactor, maybe 0.8 or 7. Okay, let me not compute the prefactor, but that's the order of magnitude. So if you express G in units where you set C already equal to 1, it's natural to think of it in that way. Now, what happens if we now do the following and say, G should be equal to 1. What it means is that we somehow redefine one of the units there. So we could say this is just a redefinition of the kilogram, so to speak. It's, by the way, the same when we already said C equal to 1. I mean, you know that when we said C equal to 1, that just means we measure distances with the same units as time. It's just a choice we make. And of course, it's a very convenient choice. And now we can somehow do the same and say by setting G equal to 1, we measure kilogram with the same units as meters. So that's essentially what's going on. So you could say, I mean, just as a maybe bracket, not remark, it essentially means that now 1 kilogram corresponds roughly to 10 to the minus 27 meters. So you could now go to a shop and, for example, order meat, and instead of saying you want to have 1 kilogram of meat, you can say, oh, I want to have 10 to the minus 27 meters of meat. What does it actually mean? So it's kind of, at least for a physicist, natural to think in that way, because it means that if you would compress the meat onto that distance, onto 10 to the 27 meters, then it would be a black hole. So that's, of course, for physicists, natural way to measure weight. And it's indeed very natural. So that's not really a joke. And we can even now say what's, for example, of course, not for meat, but for example, the mass of Earth. And actually, instead of giving the mass of Earth, I now give twice the mass of Earth. And you probably see the reason. Twice the mass of Earth corresponds, of course, to this. So, by the way, I should, of course, before I set G equal to 1, I should have written here 2mg. But as we said G equal to 1, you now know that the mass corresponds to meters, and it has an interpretation. 2 times the mass corresponds to the Schwarzschild radius. And this is maybe also something I should at least once mention. I think I mentioned it last time, but I now looked it up. I said I would look it up. In this sense, the weight of the Earth is 8.9 millimeters. Twice the weight of the Earth. But so that's now this interpretation, that's the Schwarzschild radius. So it really means that if you would compress the Earth onto essentially a ball of diameter, it would be roughly 2 centimeters or even a bit less, then it would turn into a black hole. Now one could do the same for other objects like the sun and just calculate it. I mean, you just need the mass and you need to express the mass in terms of length, which, as I told you, is natural, and then you get something like 3 kilometers. And you see already something surprising. So in some way, it seems more reasonable that you're able to compress the sun onto 3 kilometers than to compress the Earth on just essentially 1 or 2 centimeters. And this has a reason. I will just come to that. But let me first maybe give something else even. So there is, maybe you know that at the center of our galaxy, of the Milky Way, there is at least a conjectured, but I guess widely accepted black hole there. And this object that is there would have in these units this diameter. So it's a quite big thing, even if you compress it onto a black hole. And now this black hole that I've shown you, the famous one, that's in the center of another galaxy, M87. This would even have a radius, or a Schwarzschild radius of 10 to the 13 meters. So you see, even light requires quite some time, even in the case of our galaxy here, I mean, maybe a minute or more, to actually cross that black hole. So it's quite sizable black hole, and here even much more. Now, okay, I said before, I made this maybe obscure remark that it's easier to compress the sun onto that distance rather than the Earth to that. Let me make that more precise. Let's suppose, and that's a remark or a note, let's suppose before you compress the thing, it's just an ordinary object, and and let's assume for simplicity that it has a fixed density rho. Now an object with fixed density rho obviously has a mass which scales like the radius to the power of 3. Now let's suppose we compress this thing, keeping the density always the same. Of course we change the density, but keeping the density uniform over the object. So we kind of compress it in a uniform way. And then the condition when it will turn into a black hole is that 2m equals to r. Because if this condition is met, the whole mass is actually in the inside of the Schwarzschild horizon, which means we can really consider the outside as a vacuum solution, and then all our pictures here apply, and we can say there is something here, some strange event horizon, and we can take this as the definition of something being the black hole, that it has an event horizon. So now it's a very simple back of the envelope calculation one can make to just say, oh, now I can insert this into this calculation or into this formula that involves the density. And now what I get is a kind of well-known formula, and I write it down explicitly because you may see it even in half popular literature about black holes. So I just inserted this, and maybe I can even resolve it for rho. And then I find a density which is called the Schwarzschild density. The Schwarzschild density has the interesting property that it scales inversely proportional to m squared. So what does this tell us? This tells us that the density an object needs to have in order to be a black hole scales inversely proportional to its mass. So that's why I said for the sun, to make a black hole of the sun, you need much less density because the sun is heavier. And actually, let me look at this object. This I looked up here. If you calculate the density of that black hole that we know, so what's the density it needs to have in order to form a black hole? Using this formula, this density is 0.44 kilogram per cubic meter. So it's essentially like a gas. So it doesn't have to be very dense. So what one may have expected that a black hole is necessarily an extremely dense object, or an object needs to be very dense to form a black hole. That's not true. A very big black hole like this one can already form. This could have formed by just having some matter of the density of the air here in the room, just on a big enough region so that the mass is so enormously large that it forms a black hole. Of course, it's still a gigantic, it is of course a gigantic object, and that's why the density, there's this trade-off. It doesn't need much density. But the point is, a black hole is not necessarily coming from an extremely dense thing. But if you want to make a black hole out of a very small thing, out of the meat you buy, to justify why you called it 10 to the minus 27 meters, that's very hard. That's an enormous density that you would need to achieve. Okay, so that was just some maybe, yeah, that was maybe not the core of the course, but of course it's useful to know what real objects look like and how heavy they are if we introduce them into the theory. But let's now go back to understand what really this metric tells us, unless there are questions so far. Okay, I don't hear any. So, as I said, we want to study the region very close to the black hole. So in the Schwarzschild diagram, it's this line. And in order to do that, we introduce new coordinates. That's always the trick. You have already seen that in the exercises, that the trick is always to make good choices for coordinates. That was already the trick for having a real atlas of the Earth's surface. There's a lot about finding good representations of the kind of curved surface, so that you still understand how big countries are and so on. So consider region close to event horizon. And as I said, the event horizon for the moment, you should take it as being defined by the region. We'll define it in a different way, but for the moment it's just defined as the region where the Schwarzschild metric in the Schwarzschild coordinates diverges around this point 2m or 2mg if you have units in there. So now if we are close to that region, it's natural to say that we are just measuring essentially somehow a distance from that horizon. So we introduce xi as a new variable that measures how far are we away from the horizon in terms of r, so to speak. So it's just essentially a translation of r, or yeah, we translated r to another point. So it's not a very interesting new coordinate system, and we will have to do further coordinate changes. But we can already do something with it. So, of course, in the metric, we have usually this term 1 minus 2m over r that occurs. See that here? And this term can now be written, or let's approximate that term to first order. So maybe I first put everything on bracket. So now you see, if I write it like that, I essentially have xi over r. So I could write this as xi. And now, of course, I need to express r, 1 over r in terms of xi. But what is 1 over r in terms of xi? It's 1 over 2m plus first order terms, and then of course, or higher order terms. So that's just to say that if I divide by r, so if I have 1 over r in the region where r is close to 2m, I can just write 1 over 2m to first or to zeroth order, and then there are higher order terms. So in total, I have essentially an approximation of xi over 2m. So in other words, I can write the metric. So we now approximate the metric. And we have to keep in mind this is only an approximation. So G should always stand for our Schwarzschild metric. That's now our object of study. But we approximate it by a different metric. So this is really a different metric, but the point is, as long as we are close to that horizon, the two metrics somehow agree to first order. So let me write this metric. It will obviously look like this. I mean, I just get this by writing this now using this approximation that I just made. And let me in this case also write the angular terms. I mean, remember the angular terms had the radius in front, or the radius squared, and the radius squared is now approximated by 2 or by 4m squared. And then we had the metric of a sphere, which I already introduced last time and abbreviated by g omega. Okay, now we have this approximate metric. Now this metric is actually not a very convenient one for several reasons. And one reason is that this coordinate here, so let's suppose we are still outside of the horizon. So let's suppose that this xi is actually positive, so that r is strictly larger than 2m. But in this case, this here is the coefficient of the metric that measures radial spatial distances. So what it tells us is that if we move by a little step in the coordinate xi, then we move actually by a much larger amount, by something that is the inverse of xi, 2m divided by xi. So xi is not a very faithful measure of spatial distance. But the idea could be that we actually now, again, introduce new coordinates. Let's call the coordinate rho. And this coordinate should somehow more faithfully measure what's the spatial distance if we change xi. So remember, for spatial distance, I always need to even have a notion of simultaneity, but I naturally have it here because I have here a time coordinate. So the question is, if I leave t as it is and just change xi or the radial distance to the black hole, how much do I actually walk? What's the real spatial distance? And to evaluate that, of course, what I need to do is to evaluate the length of a path along or along a path that is described by changing psi and leaving the other coordinates as they are. And what's the length of a path? The length of a path, we defined this, is essentially given by g evaluated for the direction vector of the path. And of course, if the path is along the coordinate psi, I need these direction vectors, and I need to integrate over psi. Now I put here psi prime because I want to walk from 0, which is really, I mean, I couldn't really walk like that because then I'm really on the event horizon. But I can of course still measure the length of a path that I put in my diagram, which starts at the event horizon and goes up to psi, up to yes, psi. So maybe I'll put it in this diagram. If you look at the diagram, you take a point here on the horizon and just walk in this direction up to a coordinate value psi, which corresponds to a value of r, and then you measure the length of this segment here. And the length of this segment is given by the formula I just stated, where we have to integrate over a variable psi, and that's the end point. So I put a prime on the integration variable not to confuse them. Now this is a very easy integral because I can just read off this value for g. I mean, this is exactly that part here, because you see I have direction vectors in the direction covered by this part. So essentially what I get is 2m over psi. So I have an integral of 2m over psi prime d psi prime. And that's of course a very easy integral to actually evaluate. So I just get 8m. So there's a prefactor of 2 which I take into the square root from the integration. So it gives 8m psi. Let's resolve this for psi. So this was rho. So I have now a new variable, and I could also say, therefore, psi is just rho squared divided by 8m, which also means that d psi over d rho is actually rho over 4m. Okay, so these I just wrote down because I will use them, but essentially what I did is I introduced a new variable. And now in this new variable, the metric should look nicer. So let's just write down the metric using this new variable, the approximate metric G bar. So we write down G bar. Now, okay, I need to remember what G was. Let me scroll here. So, okay, you see the G bar metric here. So at the beginning we have we have just psi over 2m. Psi is now replaced by rho squared over 8m. So in total, we get here rho squared and then all the m's, that gives 16m squared, 8m times 2m. And I didn't change this variable here. So that's still the t variable. Then the next term is 2m divided by psi. Okay, what do I get here? 2m divided by psi gives now 6. I now just insert this here. So it gives 16m squared. So 1m is this one, and the other one is the one that was already here, 16m squared, divided by rho squared. So that's just the prefactor. Now I'm doing something else. I'm also, apart from expressing the prefactor here in terms of rho, I also want to change d psi into d rho. But for that, I can use this formula here, which tells me that d psi is essentially rho over 4m times rho. So I get an additional prefactor for each of the two of rho over 4m. So that comes from here, but I have two of them because I have d psi, so that's squared. And then I can now finally write here d rho. And then I still have the angular component, which I don't touch. Okay, now the nice thing, if you look at this expression here, is that it just cancels. But that's now not a coincidence. I mean, why is it not a coincidence that this cancels? And this really cancels by construction, because we said that rho it was defined, remember here, as the length of a path as we change the coordinate psi. So if you now express everything in rho, then it should directly give us the length, because it's exactly the spatial length. So what we have achieved, we have now introduced a coordinate rho, which has no prefactor here in the metric, which means it really directly measures spatial distances faithfully. Faithfully meaning that, I mean, in a strict sense, it's just one-to-one. I don't even have to apply a conversion rule. I just can look at rho and know by how far I walked on this spatial line. And as I said, walk doesn't mean that I could indeed walk. It's just a spatial line. I can never walk along a spatial line in a space-time, because I always have to move in a time-like direction. Okay. But now look at this whole metric. I mean, actually, if you look at it, you should see something interesting. And if you don't immediately see it, let me recall something, that flat space-time in Rindler coordinates. Now you see why we introduced Rindler coordinates, actually exactly for the reason that I can now write this, that flat space-time in Rindler coordinates, and I now write G, or maybe I shouldn't write GR, because it's really, so maybe G flat in Rindler coordinates looks like rho squared d omega tensor d omega minus d rho tensor d rho. If you compare the expression we got here, I mean, of course, there were also some further angular terms which I neglect from now on again, because they're not interesting. So each time a sphere. But if you look at it, we have here no prefactor in front of the rho part. Here we have also no prefactor, I mean a 1. And here we have a rho squared prefactor in front of this. So by some appropriate rescaling, it should be possible to bring this just into that form. And that's what we do as a last step. Let me do that step before the break, and then we can take a break. So let me just write omega equal to 2 divided by 4m. So that's just a rescaling. It's essentially saying we measure time with different units, which of course means that dt is now equal to 4m d omega. And now you see, if I now insert this expression here to rewrite this, okay, let me do it because we need it. Then I just get rho squared. I mean, the 16m squared will just cancel. D omega minus, and we already had no prefactor here, so that is not changed because this is completely independent of omega and t. Sorry, that was a mistake. This should be d rho. Then again, minus this other terms. So the conclusion which I want to make before the break is what we did by just doing coordinate transformations of this G bar metric is to find that it exactly looks the same as the flat metric in Rindler coordinates. But if there is a system of coordinates where two metrics look the same, they are in a sense the same. I mean, if one is flat, then the other has to be flat as well. Because whether something is flat or not is a property purely of the metric. Remember that the curvature tensor is just defined from the metric. We first take the Levi-Cheeta connection and then take the derivatives and so on. So the conclusion is G bar is flat. And that's remarkable. Let me just tell you what it means physically. It means that in this approximation, I mean, remember, we made an approximation, but we understood what approximation we made. We said we are very close here to the event horizon. In this approximation, space-time is flat. There's no singularity there. Everything is very well behaved. If we are there, things look like as if we were here, essentially in this room or in whatever room you are, and where space-time is approximately flat. Now, there will be certain things to add to that statement. of course, we have to understand what does it mean to be close enough and to what approximation is that. But it at least means that if you are in a small enough region, and that region may be very small for a small black hole, but it may also be quite big for a big black hole, we can do the whole treatment. We can understand trajectories and world lines by just studying flat space. Okay, let's leave it with that and have a short break until 1 o'clock, and then I will continue with a discussion of this approximate metric that we found, and then finally make the step to this other metric here, to the Kruskal-Szekeres metric, or to the Kruskal-Szekeres coordinates for the Schwarzschild metric. Okay, so as usual, I'll stay around for the break. So if there are any questions, it's now a good time to ask them.
I have a question about the approximation. Is it correct that with the approximation, we mean that the difference r minus 2m is much smaller than 2m?
Yes,
in
so
case
you're,
for the Schwarzschild metric.
yes, I think so. So let me briefly go back to that part. You mean this thing here? So this was, yes, so this approximation here you're talking about, I guess.
Yeah, because I was wondering if, so in case for a black, let's say a large black hole, there if we only move small distances, then we can approximate space-time by a flat space-time. But if we use the Schwarzschild metric for something that doesn't form a black hole, then in a good approximation, space-time is also flat. For example, or just a feather, for example.
Yes. So actually, I mean, what you see here, what is relevant in some way, or already here, is that how much smaller is Xi than 2n. And essentially, independently of whether you are now close to the black hole or to the event horizon or even outside, it's always true that if you are in a, I mean, or maybe more generally, what we will see is that the curvature of space-time in of a Schwarzschild solution is such that it will, it's singular at the center. I mean, whatever we call center, we will come to that. But then it will decrease as you move away from the center. And when you are in the region of the event horizon, you are already quite far from the center. So what does it mean to be quite far? It just, independently of whether there's a horizon there or not, it turns out that if you move by distances which are much smaller than essentially the distance from the center you have, then you can, to good approximation, consider that as flat space. And so we said last time that if you're far away from the black hole, we can also approximate it by flat space. So this approximation is always, I mean, in some way, it's not quite maybe a correct statement when I say if you're far away, you can really approximate it by flat space. I should add that if you are far away and if the distances, let me make a more general statement. So whenever I talk about something is large or small, I should always be careful and compare two things, because something being large doesn't mean anything. I mean, if I tell you the speed of light is large, that actually doesn't mean anything. What has a meaning is the speed of light is large compared to the velocities that we usually consider when we drive, or when we sit on a bike or so. Now, if you are talking about distances, you should also compare it. So the statement should be that if you're far away, compared to the distances you are now, let's say the size of your lab, then you can, to good approximation, assume that within that lab, space-time is flat. And so in a sense, we are doing the same here. So we are saying, okay, we are now close to the event horizon and we are just moving around by distances which are much smaller than the, let's say, in this case, the Schwarzschild radius. And in this case, again, we can, as long as we are in the lab that is that small, make this approximation. This could be itself, of course, be like something that compared to us has to be very small. So maybe if you look at the exercises, there was something about the sun, or a black hole of the mass of the sun, and then there, when you would be a human-sized object on close to the event horizon, would actually feel very strong tidal forces. Tidal forces are essentially the forces that you feel that that origin from the deviation from the flat approximation. So whenever you're in flat space time, you have no tidal forces, and tidal forces come in because you have curvature, and therefore essentially you're torn apart or squeezed together. And so on. This region, like if the, like in, yeah, you saw here before, the sun has a relatively small Schwarzschild radius, and now if you are 2 meters big, that's actually not so small compared to 2 kilometers. It's still small, but not that small. So that's relevant. Of course, one has to put in prefactors and ask what approximation do we mean and all that. But maybe my point is we should always compare to something, like small compared to what. And here we compared essentially small compared to the Schwarzschild radius. I'm not sure this answers your question, but please feel free to make it more specific.
I quickly have to think about your answer, and maybe I'll ask after this second lesson.
Yes, sure, yes.
Again.
You're
Thanks
welcome
a lot.
to do that. You're welcome. Are there other questions that people are curious about or want to ask? Adrian, was there anything in the chat that I should answer?
There is a question about whether this means that we can approximate the outside of the event horizon as flats. And well, the answer is you can always approximate every small enough space by time patch.
Yes, right, yes. Yes, yeah, that was maybe a similar question. So indeed, I shouldn't, maybe it was a bit misleading when I said last time. Maybe let me kind of correct that sentence. Last time I said, far away from the black hole, we can approximate space-time by Minkowski space. So this is only true in any small enough region. So if you are away from the black hole and you are in a region which is small compared to essentially how far you're away or something like that, then you can do this. But if you, for example, say, oh, now I'm far away, but now I'm really looking what happens if I make a huge circle around the black hole at that distance, then you may encounter global phenomena that are no longer subject to that approximation, because the approximation would only hold as long as you stay in this small room, small compared to the radius, which could still, of course, in practice be a big room, but certainly not one where you encircle the whole black hole. Okay, if there are no other questions, I think it's almost time to restart. So what we have seen is that space-time can, in small enough regions, be approximated by Minkowski space. And now we are going to exploit that a bit. Okay. So the idea is that we essentially do things in reverse that we did last time when we talked about Renner coordinates. When we did the Renner coordinates, we started with so-called Minkowski coordinates, and then said, in these coordinates, if you have an observer who is constantly accelerated, then more convenient coordinates are the Renner coordinates, and then the flat space-time metric looks like this. But now we can say, once we had some initial coordinates. I mean, now we didn't go by this flat thing. We introduced rho in a different way. Remember, we introduced it as kind of a distance from the event horizon, and the omega was also introduced essentially just as a rescaling of the time. So we have these coordinates, but we could now say, let's now do the opposite transformation. So instead of going from Minkowski to Rindler, we kind of apply the opposite transformation to turn these coordinates into something that looks again like the Minkowski coordinates. So that's the idea. So the idea is to essentially go back to Minkowski coordinates. And please remember that all we are doing now is valid in this approximation, where the approximation is that the distances we travel are much smaller than 2gm, than the Schwarzschild radius. Now remember how we actually defined the transformation between Rindler coordinates and Minkowski coordinates. That was essentially this transformation rule that I'm just writing down here. And remember, by the way, x is then always larger than 0. So it's kind of a certain region in space-time. And let me just mark these two equations with a star because I want to refer to them a bit later. So what we could now say is that we have now made several transformations. So we somehow started with something, namely with space-time coordinates from Schwarzschild, and then somehow said, let's somehow consider a certain region and then go to rho. And now we again do a transformation to t and x. So we have a sequence of transformations, but ultimately we are still talking about the same object. So we can now say it's still the black hole that we are describing, but we have now coordinates that we call t and x. And just for you to make the link to this initial diagram, these will be, the coordinates I have here are now Minkowski coordinates. They're not the Kruskal-Szekeres coordinates, but we will see, and that's why I did all that, that in the region close to the event horizon, they coincide up to a constant factor with the Kruskal-Szekeres coordinates. So when what I now draw here will essentially match this diagram here whenever I'm close to this diagonal here. That's the idea. And then I will just say, of course, we can extend it, and that will then make things more complicated. We can no longer assume it's flat, but in the region of that, it's really flat. Now we have to, again, I mean, at the beginning, I just told you the event horizon looks like this. Now we can actually make sense of that. So what does the event horizon, where should it be? The event horizon, of course, corresponds to the, I mean, let me maybe first remark something, because otherwise this is not clear. So in this metric, we have seen that x squared minus t squared is always equal to rho squared. Now, if we are close to the event horizon, we can never make rho 0. Remember the metric we started off with, which was the Schwarzschild metric, is only defined for positive, for r strictly larger than 2 mg or strictly smaller, which meant by this coordinate transformation that the psi had to be strictly positive or strictly negative, and correspondingly also the rho, which of course depends on psi, has to be strictly positive. It cannot be 0. But we can nevertheless think of the region where rho goes to 0, where it's arbitrarily close. And in this particular case, of course, x squared minus t squared is essentially 0. Which means that we can say that x, and remember x is positive value here because it's cos h, and cos h is always positive, x can be equal to t, or the negative, if t is negative, it's the absolute value. And that just follows from essentially solving this equation, this quadratic equation. You have two solutions. X can be positive or negative t. So, but what's actually the interesting thing about rho equal to 0? That's the event horizon. So what I calculated here is just a condition for how the event horizon looks like in this diagram. Let me use the same color that I used before. So the event horizon is therefore this diagonal as well as this diagonal down here. That's what this equation here tells us. Okay, so we have already identified now the first thing I just claimed at the beginning, namely that there are coordinates in which the event horizon looks like this. Now there's another interesting thing to remark. Because we are in Minkowski coordinates, the metric is of course trivial. We already know that. So in Minkowski coordinates, trivial in the sense that it's the eta that I introduced last time. So the G is equal to 1 minus 1 minus 1 minus 1, which in particular means that all light cones just really look like 45 degrees thing. So that's true everywhere in Minkowski space. And so now for the approximate metric, it's just true everywhere. So these are light cones. And this is the positive time direction. It's this inner part of the light cones. So that explains, because I said Kruskal-Szekeres will be the same close in the vicinity of the black hole horizon. We will just see that, that we can indeed draw these light cones as I did it at the beginning. At the beginning, I didn't justify it, I just drew them. But now we can understand that the light cones have to look like this, because it's just Minkowski space. But once we understand the light cones, we can of course say, yes, trajectories can just move within the light cone. So there could be a trajectory like this. So this is actually the world line of someone who crosses the event horizon. And by the way, we can call this here the inside or interior region of the black hole. And that's the exterior region. So the green world line corresponds to an observer or a particle or whoever who actually falls into the black hole. So he crosses the separation between the exterior and the interior region. And you see that there's really nothing special here happening, because the metric expresses everything. Maybe there's something else happening that has nothing to do with GR, but according to GR, everything is set by the metric. And the metric here is completely flat. You have the nice light cones. Even if I could even kind of think of a watch. So if I have an observer with a clock, these would be the ticks of the clock, and the ticks would be in this metric essentially equally spaced. That's also what the Minkowski metric tells me, that if I have a trajectory which is more or less going in the time direction, then the ticks of clocks are equally spaced. So that's what happens to someone crossing the event horizon. So essentially nothing happens. Nevertheless, it's kind of, as I said at the beginning, a point of no return. And what does that mean? Remember, these light cones are they define the causal future. So whenever you are at the point, for example, here you can only reach things that are within the light cone. And it's now quite obvious, because the event horizon itself is a 45-degree line. Once you are inside, there is no way you can ever move outside again, because you can only move here within the light cones. So in that sense, it's really a point of no return. That's now obvious. That was not clear from the diagram here. This diagram wasn't even clear whether we could get inside. Here it's from the new coordinates, you can see clearly someone can cross without harm the horizon. The only maybe bigger problem is that he cannot return. There's just no way out. But a point of no return is really something that is globally defined. That's not, and that's important to notice. So there's no local property that would ever tell you that this is a point of no return. This is a bit like for other points of no return. I think there's a nice example by, I think it's by Lenny Susskind, who usually talks about water flows. And imagine that you are on a big river that flows towards a waterfall. And let's suppose the river is a bit faster than you can swim. Now, if you're far away from the waterfall, you can still get out. There's still ways to get out if you start early enough to swim against the river and maybe sidewards. But there is somewhere a point where, given the velocity by which you can swim, there's just no way you can ever evade the waterfall. But this may be long before the waterfall, if you're in the middle of the river. So there's nothing that happens to you at that point. And maybe you realize it at that point, and that may be bad enough, but there's nothing physically that happens to you. And that's the same here for this point of no return. So crossing the Schwarzschild or the event horizon of a black hole doesn't mean that there's anything bad happening to you. Of course, if you're a good physicist, you can then do the calculation, know that you will not escape ever. But that's another thing. Okay, now let's...
Sorry?
Yes?
Sorry, question. What about the other purple line at the bottom?
Yes, I will come to that one. That's a very good question. Let me answer it in maybe towards the end of the lecture, if that's okay for you.
Okay.
Okay, now I think that yes, the other thing that I should maybe mention in this context is that there is still I mean, I could have said that already earlier, but if you look at the Schwarzschild coordinates, so let's go back here, and if you look at the ticks of a clock there, then how does it look like in this picture? So we could now somehow try to go back and see, okay, now as we know that there are trajectories of, let's say, people falling into the black hole. So this exists, this is a valid thing, that's what we just derived, not yet with Kruskal-Szekeres, but with coordinates that approximate that very well here. Then this world line must have a representation in the Schwarzschild coordinates. So what does it correspond to? Now you can do the calculation, I mean, or you can even see it pictorially. I will now not do it in detail, but it's clear that it has to be a line like that where at least you get closer to the Schwarzschild event horizon. But how can this now be matched with the fact that we said, what I just said, and hopefully convinced you that if this person here has a clock, then I could have here the ticks, and after a finite number of ticks, let's say if you start the clock here, then 1, 2, after 3 ticks, the person is inside the event horizon. Here, if you have this line here, then it doesn't look like it will cross the event horizon after a finite time. However, that's just now, again, a coordinate artifact. So maybe the first tick here corresponds to that one here. And then there's maybe a second here. But then the only way to escape a contradiction is to say all the ticks will now become more and more distant in this diagram. So maybe the next tick is already here somewhere. And the next one doesn't even exist any longer. It's so far out in the future. So maybe if I would have drawn more here, say I have now twice as fast clock, there would be maybe a tick here and here, and the next one may be somewhere already up there where my paper ends. So in other words, what we can say is the following. If this is a good coordinate system for an observer who is far away from the black hole, and this observer would now describe what happens if someone falls into the black hole. So let me maybe get rid of the other green lines here and just keep that one. So the idea is that this green line corresponds to that one. It's just a different chart. And this chart is the chart that is natural for someone far away. And remember, far away, it really corresponds to good approximation to Minkowski. Therefore, this time axis really corresponds to the clock time shown by someone far away from the black hole, to us, for example. So let's suppose this is the diagram where t corresponds to our time, and now we see someone or some particle, or let's say someone with a clock falling into that black hole. And this someone with the clock is this person with the green world line. And let's suppose this person sends out the signal each time the clock ticks. So here sends out the signal, here, one here, and so on. But you see, the person will only send out 5 signals ever. I mean, he will send out more, but these signals clearly can never reach us. So these are already beyond the horizon. They're not even drawn in this diagram. This diagram just stops there somewhere. So what it has to mean is that the signals that we will receive become more and more distant in time. So we would actually see that signal, then it will take some time until we see that one. It will take even much more time until we see that signal. It will take years until we see that signal, and maybe millions of years until we see that signal. So we will never see the person actually passing the event horizon. We will just see him slowing down. And actually slowing down means that it will disappear for us, because there will be an enormous redshifting. So all the light coming from the person, if the person still, let's say, has a reflects light or has a light source, all that light will be enormously redshifted for the same reason, because everything from our perspective goes much slower. And so an extreme redshift also means that the energy that will essentially be emitted by the person will become less and less. And at some point, it's so little that there will be no, I mean, if you now think of quantum mechanics, there are, of course, units. There's not kind of a continuum thing. We will either see a photon or not. And at some point, we'll just no longer see any photons. They will become more and more sparse, redder and redder. And at some point, we will see nothing. So we will never see someone entering the black hole. It will just disappear in that sense. So it will be enormously redshifted, but we will only see the person up to that point. Whereas, so we wait forever. We will never, for our so we will never reach a time when we can say the person is now in the black hole. Because when the person here reaches the black hole or the event horizon, this is in this diagram so far up that everyone else is no longer existent. So for us, it's the infinite future in our time measurement, in this t-scale. It's the infinite future when the person who has here the clock, so this is a natural diagram for the person who falls in, thinks he has now passed the event horizon. So in other words, if you fall into a black hole, once you have passed the event horizon, it's an even worse time. I mean, I told you it's a point of no return, but it's not only that you cannot return because you're too weak to swim backwards, it's actually that the whole universe outside in a way has already ended in some way. I mean, in the way I explained it to you now. So the time has already passed. It would be the infinite future already of everything outside. So the event horizon is really an extremely interesting object. And the other thing we can learn from this diagram is that the event horizon is really not a spatial region if you're close to it. If you are far away from it, it really looks like a spatial region. It's really this little sphere here. But if you're close to it, then it's not something that looks like a space. It's more like a light ray. It has the property of a light ray. And that's, again, why we had these Renner coordinates, so that you can understand what such lines here mean. So once you are close to the event horizon, it's something that comes towards you at the speed of light. And the only way to escape once you're still outside is to accelerate enormously hard. And that's exactly the same acceleration that we discussed when we discussed the Renner coordinates. I remember this diagram looks a bit like the Renner coordinate. I even told you that there is somehow a horizon in some way. And the trajectories of people outside look like this.
There are some questions in the chat.
Yes, please.
There's a problem with the understanding of what the diagram here is. So one misconception is that people think that the length of this line you draw is actually the length of the curve. This is not true. You would have to calculate this with the metric, and you would see that if you integrate this line all the way to infinity, you will get a finite value.
Yes.
Also, if you would continue this line, the line would come down from infinity and hit the t equals 0. And yes, this also does mean that it passes, because both lines added together will give you a finite value, even though this goes all the way to infinity. And this will mean that you will reach t equals 0 in a finite time. So it does cross the event horizon. It's not that it does not. And yes, if it would really not cross the event horizon in another coordinate system, this would be a contradiction. but it is not.
Yes, right. Yes.
Just
So
a
thanks
very
for
dangerous
answering this already.
picture.
Yes. So it really all shows this is just a bad diagram. And what Adrian just said, you can also actually see in the formula that we have here. Because if you look at what this formula tells you, then it's exactly what he said, namely that if we move upwards here and ask ourselves how much time passes here, then it's a bad idea to think this is somehow related with the length of the curve on the diagram. That you should never do a priori. You have always to take into account there's a metric behind it, and the metric tells you how long things are. It's like when you look at the chart of the world atlas and see that on the North Pole there are very big continents, and then you go to an actual globe and see they're actually not that big. They're still pretty big, but not expanding over the whole Earth almost. So that's the same here. It's something that looks very big is actually not that big. And how do you see it? I mean, the distance here between two ticks, or maybe the one here and the next one, which I said is far above in infinity. So this distance has to be calculated via this formula. And you see, despite the fact that you have to vary the t-value enormously, so you have to, this formula tells you have to increase the t-value enormously to only get a little bit of length. Because this prefactor b, so if r is close to 2gm, then this prefactor, which I called b, is very small. But if the prefactor here is very small, it means in order to actually get real length is what the g tells you. That's not what t tells you. T is just a diagram, it's just a parameter. You have to increase t enormously. And actually, if you're infinitely close to the event horizon, you have to increase t infinitely. So that's just another way to say what Adrian before just already said when he answered the question, that the lengths here, the real lengths are different than what you see on the diagram. So what looks here enormously long is actually, according to the metric, just one tick. And the problem is that it really diverges. Okay, I hope this clarifies that, but that's certainly something you should not hesitate to ask questions, because if you see that for the first time, then it's almost certain that you have certain points that you find unclear. So please feel free to ask. There are certainly not stupid questions here. There are never so far, but I'm sure here there are questions that may sound maybe stupid because you're talking about people falling into black holes. But at the end, it's really about the understanding of, really have to now take this really very serious, that a diagram, a chart is only a chart, and the real distances and the real times that pass are given by these expressions. And that may already help. So you shouldn't overinterpret things. The reason why I was allowed to here draw ticks that are equally spaced is that here, I said we are in Minkowski metric as long as we are close to the event horizon. Here we are not, and we have to take this into account. Okay. So now, you may also, it may maybe take you some time to even think of a good question. So I'm also happy to answer questions, of course, next week, and we can come back to that, because I think it's important that you really understand this thing. It's kind of one of the most intriguing, but also most basic examples of an interesting space-time. Interesting in the sense that it's not only a bit curved, it's really curved in this extreme sense that in certain coordinates, naturally seeming coordinates, time and space coordinates change their roles. And that's here the case. So now let me just nevertheless briefly continue and tell you what are now the Kruskal-Szekeres coordinates, which I mentioned at the very beginning of this lecture. So let me first just to simplify my own life, introduce an abbreviation. So I will often use a particular function of R. R is now, again, the initial parameter so we start again, kind of restart with the Schwarzschild coordinates, and R is the parameter of the Schwarzschild coordinates. And now I can just define this function of R. which, by the way, I could also have written with Xi, because you remember Xi is just a translated R. So let me write this. I think it would look like that roughly. Okay. Now, let me, before I now use that, because if I just define a function, you may not have a good picture of what this function should be. So let me make remarks about particular properties. So if I look at this function in the region where Xi is very small compared to 2m, in other words, where this is equivalent to say that R is in some way close to 2m. So in the region where I'm again close to the event horizon, there we see that Fr is very well approximated by R over 2m minus 1, because this exponential will just be essentially close to e to the 0, which is of course just a 1. So we can think of this function as one that is essentially just, again, is essentially the identity, or giving us again this prefactor that we already know, the Xi over 2n, which is, remember, I just write it down for convenience, related to the rho that we also introduced before in that way. So that's one remark about this function. The other remark I want to make is that if I look at the region where R is very small, so this is really close to the singularity. So if I let R go to 0, then this function just tends to the e to the minus 1, or minus e to the minus 1. And you can immediately see that in this case, I have here this factor goes away, this one as well. So I have just e to the e minus e to the minus 1. Okay. Now after this, these remarks, let me finally now define that metric, that these coordinates, and the coordinates are just defined via a coordinate transformation starting from, or I define it in that way. Of course, you may define it just by stating the metric, but I now give the coordinate the chart transformation map, so to speak. So in this picture here on the right, it would be the map here that we always looked, we always considered such chart transformation maps when we talked about manifolds. This is now a one that is relevant for physics, the one that goes from Schwarzschild coordinates to Kruskal-Szekeres coordinates. And it has all elements that you may think are quite familiar. So it looks a bit like the transformation from Rindler coordinates to Minkowski coordinates, except for this prefactor here. But remember, the prefactor here is kind of quite natural in the sense that at least close to the horizon, it's just what we already saw before. It's close to rho squared. But this is now not always, this is now for the region where R is strictly larger than 2m. And remember, we actually had, strictly speaking, two Schwarzschild charts. The other one is the one where it's the opposite. And there, indeed, you can easily see the function becomes negative. And therefore, in order to take the square root, I need to put the minus sign to even make sense of this. So here is the definition again of the function. And you see that it becomes negative if R is smaller than 2m. And now what I do here, I also exchange the roles of cos h and sin h. So that should be the chart transformation if R smaller than 2m. So you may now ask, why is it defined like that? And essentially, you have now two different reasons. At the end, you can define any chart. There's not a physical reason. So remember, first of all, a chart is always something artificial, something we made up. But I have now two motivations. One motivation was given in the exercises, and I don't want to go into that now. but you can look at the exercises essentially to see why we arrive at this transformation in a natural way. The other is the one I now gave in this lecture, which is that we want to have a chart which is well behaved in the region around the event horizon. And remember, we achieved that and we found something of that form here. And you see it kind of matches this. If you take into account that FR in this region where we did the approximation, which is exactly given by this condition here, FR is equal to rho square over 16m squared. So if you insert that into this whole thing, then of course the square root of this gives you exactly rho over 4m. So the 4m cancel and you just have a rho here. So indeed, the thing that I marked with a star somewhere, so let me try to find it. This thing is actually exactly, if you also take into account this definition of omega, is exactly matching the transformation I gave you. So let me write this, that note for r close to 2m, this matches star. So in other words, the whole motivation that I gave you also motivates this transformation, at least in the region close to the horizon. Now, the problem, why did I just not stay with that one that we already had? So remember, this was only for, this only worked for our approximate metric G bar. So the G bar is a nice approximation in the vicinity of the event horizon, but generally, of course, this would not work if we are away from that. So you could understand this Kruskal-Szekeres coordinates as coordinates which in the vicinity of the event horizon have the same properties that we wish to have and actually derived, but also extend to other regions. They also extend further. And now, of course, this extension is not uniquely determined. You can, if I tell you what the metric should be or what the coordinate should be close to this line, you have still a freedom to kind of extend them in an arbitrary way outside. But the extension is chosen in a particular way that, again, has a nice property. And that's what you can see when you calculate the metric. And I said already at the beginning that I will not do the calculation of the metric in, it's still the same metric, it's the Schwarzschild metric, but I will not calculate how it looks like in these coordinates. That's something you can now easily do. And in particular, if you did the exercises, you should already be familiar with that. It turns out that the metric in these coordinates, the Schwarzschild metric in Kruskal-Szekeres coordinates, looks like this, where, okay, now I did a bit of cheating. I now use t and x, but in the metric I still wrote an r. So I have to regard r as a function. Let me define it. R is a function, of course, of x and t. And it's actually just given by the inverse of this function that I defined before. So this is just, if you look at how x and t are related to r, and this, if you have x and t, you can again retrieve r. So this is something I just state now, but the point I want to make is that this is actually, again, something that looks nice. Why is it nice? If you look at this bracket, then you see that there's the same prefactor, which is here, in front of the time coordinate and the radial coordinate x. And this is the distance coordinate, how far you're away from the center. And then you have, of course, the angular coordinates, which are always the same. So if I have the same prefactor, then this means that if I ask what are the zero vectors, what are the light-like vectors, they are the vectors where the t component and the x component are equally long, because then these cancel and you get a zero in the metric. So in other words, this metric or these coordinates, the Kruskal-Szekeres coordinates, really have the property that not only in the vicinity of the horizon, you have a Minkowski, I mean, that's only true there, you have the Minkowski metric, but in the Minkowski metric, we saw that the light cones are these 45-degree lines. But now in these coordinates, this is true everywhere. So the light cones everywhere look like this. So in other words, this diagram has a very obvious causal structure, and that's why they are nice coordinates. So again, that's not a physical motivation. You can take coordinates at your wish, but the Kruskal-Szekeres coordinates are coordinates which have the property that light always, wherever you are in the diagram, moves at a 45-degree angle. And that makes it very easy to think about, for example, causal future. I mean, here we were not sure in which direction do things move, whereas here we always know they move upwards or in angles towards the vertical that is less than 45 degrees. Okay. So now as we have this kind of these nice new coordinates, we can now try to explore a bit more what they tell us. So we can now try to look at this picture and from that picture learn more about the black hole. So maybe the first thing we could now start to talk about, which we couldn't before, is what about the event horizon, and not what about the actual singularity where r is equal to 0. So if I briefly go back, then in this picture we have of course the region where r is equal to 0. And I already told you that at r equal to 0, the curvature is actually diverging. So this is really not just a coordinate artifact. But the question is still, how does this blue line, how does this singularity look like in these coordinates? So this is really in some way what you would call the center of the black hole. But you will just see that this is maybe a bad terminology, call it the center, for a reason that will become clear in a minute. So let's consider the singularity. So the singularity is essentially defined by r equals 0, or close. Maybe I shouldn't say equal 0 because that's no longer on the chart. But if I make r arbitrarily close to 0. So by the way, I forgot to say that, of course, when I said here r is smaller than 2m, it should still be strictly positive. Because if it's not strictly positive, we have here some troubles. Okay, actually, the trouble is here that, let's see, yeah, maybe it's not even obvious from the diagram. So the trouble will be that if we calculate the curvature, it will diverge. Now, I'm not sure, it should actually also be obvious from the metric that something bad happens there. But yeah, okay. That's now not completely obvious to me. I'll have to think about that. Anyway, so let's be on the safe side and not put in 0, but let r go to 0. So what does that mean? If r goes to 0, this means that t squared minus x squared are equal to, now we can try to calculate that. So let's look at our coordinate transformation. So maybe we should now look at this part here, because that's the part where r is smaller than 2m. And of course, if it approaches 0, this is the relevant thing. So if I want to know what happens at r equals 0, a good idea is to kind of get rid of this time dependence. And one way to achieve that is to calculate t squared minus x squared, because then this term and this term will just subtract to 1, and I'm just left with this thing here. So in other words, t squared minus x squared is 4m squared times what is in the square root. So let me write this. 4m squared, I think, and then the square root squared. So in the square root, we have this function of f, and I think we should, and f, of course, of r. It's probably a minus, I guess. I'm confused. It shouldn't. Oh, no, yes, it's a minus here. But we know, and that's why we looked at these properties. So fr for r very small is minus e to the minus 1. So I was first confused why there's a minus, but the minus cancels because if I now insert this, so if I now really let r go to 0, then I get here just e to the minus 1. And now we have a nice equality. So we have essentially identified the region in terms of the t and x coordinates in which r becomes 0. And this region is essentially given by an equality. This is equal to some constant. So this is a constant. And of course, you can see that this just in the diagram corresponds to essentially a hyperbola. So maybe I should draw a new diagram because otherwise I squeeze too many things into our old diagram. So I'll now redraw the diagram here briefly to put some more elements into it. So we have the t-axis and we have the x-axis. Now there is, again, the event horizon that is 45 degrees. And now I already actually extended it a bit. And I will just come to that. That will also answer the question I asked before. But let me first draw the horizon. So the horizon corresponds, so let me make it blue. Maybe just on the line. So this means that we are essentially on a hyperbola here. So usually I draw these horizons with wiggly lines. And you see from this equation that there is another solution. There's also one where t is negative, and we get the same. So there's actually another horizon, another singularity here. So this is the r equals 0, and here is again r equals 0. There are actually two different regions. Now I said before, if you did the coordinate transformation, that this here will always be, or okay, I should go up a bit. So when we, where was it? Somewhere I did, yes, here. So here I said x is always positive. So remember, this was just because we anyway said we are close to the event horizon of the black hole. Now in the derivation of the Kruskal-Szekeres coordinates, as I said, you don't need to necessarily start from the Schwarzschild and then go there. You can immediately, I mean, once you have realized that these are good coordinates, you can take these coordinates and just solve the equations, the Einstein equations, and get a solution. And then it turns out that this solution is actually encompassing a larger part, a larger manifold than the one that was covered by Schwarzschild. So, of course, it's larger because it includes this event horizon, but it actually turns out it covers much bigger regions. So we can, in these charts, find solutions that even extend to the negative x thing and into regions like this region here, which we didn't cover from by starting from the Schwarzschild coordinates. So in other words, if you just take the Einstein field equations and solve them and look for the largest possible manifold that solves it, then it turns out that in the Kruskal-Szekeres coordinates, you cover an enormously big part, and the part that was covered by the Schwarzschild solutions were essentially just this region here and this region here. These were the two, maybe I should draw it with different colors. So that's maybe the green region, and then let's, okay, maybe I'll use some even more different colors. So let's this is a region, and that corresponded in the Schwarzschild 1 to whatever is here. And then we have another region, which is this inside, and that corresponds now here to that region. But in these coordinates, we see that purely mathematically, there are more regions that are valid solutions of the Einstein field equations. And one can now ask what these mean, but at least they have names. So that's still the exterior region. That's the interior of the black hole. Now the region downstairs is called, and this is a priori just a name, interior of the white hole. So it's just a solution that pops up. It's not that we have seen an object like a white hole. And this is called the parallel exterior region. Now, if you find a solution mathematically of something that, of some equation that was stated, like the Einstein field equations, then it's not clear that this solution corresponds to anything real. So the statement here is just that there is a manifold, a very big one, which is somehow not only describing what we would expect to be a black hole and the black hole horizon, which would be that part, but it's somehow describing more stuff that we haven't even matched to anything that we have observed so far. Now, there are many discussions about what these regions means, whether this is now a parallel universe or whatever. Notice that they are not causally connected. So if you are in this yellow region here, you will never be able to reach this parallel region here. That's not the other side of the black hole spatially. You cannot get turn around. So you should not think in that way. That's really a spatially distinct region. And then we have a region here as well. Now I should maybe mention one thing. What we have done when we solved, or I mean, we haven't solved the Einstein equations, but the solution of the Einstein equations that leads to the Schwarzschild metric assumes that in a way that the configuration that led to the black hole was always there. It's also called an eternal black hole. But of course, real black holes form at some point. So when we talked here about a black hole in this initial diagram, this line just extends here into the infinite future, but also goes into the infinite past. So it's as if the black hole never formed. It was there from the start. This solution here also corresponds to that. So this things we get, like this white hole part, correspond to situations where things were always there, which is maybe very unphysical. So there are good reasons to believe that this part is just a mathematical artifact from assuming that things were always there. And we will later in this course discuss how black holes form, and then we'll see that the relevant part of the diagram is essentially this part here. So that hopefully answers also the question what that is. So that's somehow the horizon of the white hole. So the white hole mathematically is a region where things can only escape. So this point of no return is essentially, or this line of no return is similar to that one, except that you can only get out and never get in back. But as I said, it's not clear whether this corresponds to anything that is physically real, at least not to our current knowledge. Okay, I think that was all for today. That was maybe quite a lot of stuff that you may require some time to just get an intuition for, because I think it really helps to stare at these diagrams and to ask questions about what, if you are on a world line going towards the black hole, or if you stay outside. And maybe I will devote the first, let's say, half hour of the next lesson to discuss that a bit more, because yeah, I think it's worth understanding different scenarios. Also in view of something I want to do towards the end of this course. In the very last lecture, I plan to discuss a bit current research, and there we have the so-called black hole information paradox, which has to do with the fact that if you cross here the event horizon and kind of hit the singularity, then it looks like you are lost, and all the information you you took with you is also lost forever. Now you could say, okay, it's just lost because it's somewhere else. But we also know that black holes evaporate. So at some point, the black hole is no longer there. That's a different effect. That is Hawking radiation that involves quantum mechanics. And that leads to an apparent contradiction, because it seems like you can throw things into the black hole and then the black hole evaporates and the information was really gone. So you can destroy information. And that contradicts a postulate of quantum mechanics, namely that all processes are unitary and therefore information can never be fundamentally lost. And that apparent contradiction, which is called the black hole information paradox, is something I would like to discuss. And as a preparation, it's good to think a bit more about these trajectories of people falling into the black hole. So that's what I'm going to do next Tuesday in the first part. And then we will most likely have to return a bit to the mathematical side and learn about integration on manifolds. Okay, that was it for today. I wish you a nice weekend and hope to see you back next week.